Good morning, good afternoon, everyone. Good night. I'm Valentina, I'm the YESS officer. And today we have the first webinar of this second edition of the GAWTEC webinar series. And the focus on this webinar series will be reactive gases. Today, our speaker is Lucy Carpenter from the University of York. Before her presentation, we will have a brief summary of who is organizing this webinar series. Next, please. But before that, just a briefly reminder of the code of conduct. Please be polite and respectful to all the participants and all the speakers. You will be muted and you can access to your video right now. But you are able to type your questions in the chat box during the entire presentation. So during Lucy's presentation, you can leave your questions, and then after her presentation, we will have a Q&A session, and your questions will be answered. And as you see, we are recording this meeting, and we will upload the video to YouTube in the upcoming days. So now I give the floor to Claudia. She will present GAW.
Hello, everybody. My name is Claudia Woloschuk from the WMO Global Atmosphere Watch program. And I'm sure you will be convinced after this webinar by Lucy that atmospheric chemistry research is extremely important. Thank you very much, Lucy, for doing this. Just briefly, who we are. So the Global Atmosphere Watch program provides international leadership in research and capacity development in atmospheric composition observations and analysis. This is done through long-term systematic observations of chemical composition and the related physical characteristics of the atmosphere. This includes quality assurance and quality control and the development of products and services of relevance to users. And we build on partnerships involving contributors from many countries. GAW focuses on a set of variables that you can see here. So it includes UV radiation, stratospheric ozone and the vertical ozone distribution, greenhouse gases, reactive gases that we will learn more about in this webinar series, total atmospheric deposition, and aerosols, which is in total about 60 variables that are taken care of by GAW. Currently, we are in the implementation plan from 2016 to 2023, and the vision for the next decade of GAW is to grow the international network of high-quality atmospheric observations across local to global scales to drive high-quality and impact science, while co-producing a new generation of research-enabled products and services. And a very important component of all of this is, of course, capacity development, of which this webinar series is part. And with this, I will hand over to Sonia to explain us what is the GAW Training and Education Center.
Yeah, hello, everyone. I'd like to introduce GAWTEC to you. GAWTEC stands for the Global Atmosphere Watch Training and Education Center. The GAW community has set high data quality objectives that should be met by all participating stations. Therefore, training and education are an integral part of the GAW program and critical to its long-term success. And this is why in 2001, the GAWTEC Training and Education Center was established. We had our 20th anniversary this year after 37 successful courses with over 400 participants. GAWTEC is located at the Environmental Research Station Schneeferner Haus at Germany's highest mountain called Zugspitze. Training courses are offered twice a year. For each course, 10 to 12 participants are invited for a 2-week session, and each course deals with a major topic covering all relevant parameters. Please, next slide. If you're interested, you can visit our website with a lot more information. It's gawtec.de. And I will hand over to Fatin, who will say something about the YESS community.
Thank you very much, Sonia. Thank you, everyone. Hello, everyone, and welcome to the second edition of the GAWTEC webinars on reactive gas. I'm Fatin Atik Bahar from the Young Earth System Scientists Community EXECO, and I'm very glad to give and to say a few words about the Young Earth System Scientists Network. Who we are. YESS community serves to help share the future of Earth system science by fostering international and transdisciplinary leaders of tomorrow to develop the research vision that can serve an equitable and sustainable world. YESS community is widespread all over the world. So we have a community of more than 2,100 members representing 120 countries. And we have several working groups. As you can see in the figure, we have science working group, the outreach working group, who is empowering this webinar series, the membership working group, and also the online working group. So we can find here all details on how to reach out to us. You can find our all announcement on our social media, on Facebook, Twitter, LinkedIn, and you are also welcome to contact us anytime. So thank you very much. And I give back to Sonia.
Yeah, I'd like to introduce our speaker today. We have Professor Lucy Carpenter with us from the University of York. Professor Lucy Carpenter is an expert in atmospheric chemistry. Her research projects include atmosphere-ocean interactions and also long-term atmospheric composition. Lucy is a co-founder and also the UK principal investigator of the Cape Verde Observatory, which is also a GAW global station. And today she will talk about reactive gases in the atmosphere and impacts on climate, human health, and the ecosystem. Lucy, thank you for being here today, and the stage is yours.
Thank you, Sonia, and thank you everybody for the nice introduction. So I will try to share my screen first of all. Let me go to the first slide, and hopefully everyone can see that okay. So yes, welcome everyone to this first webinar on reactive gases, which is the start of a series over the next couple of months on atmospheric composition and measurement techniques related to reactive gases. So it's my pleasure to really kick this off with, I suppose, an explanation of why these gases are important to measure. They really are fundamental for many aspects of atmospheric science, for climate, human health, and ecosystems. And this is despite the fact that they represent only a very tiny fraction of the atmosphere. So you're probably all aware of this kind of picture of the atmosphere already, where nitrogen makes up nearly 80% and oxygen around 21%. So that doesn't leave very much for all of those other gases, and there are millions of other types of gases. So we're really looking at very small fractions of a percent for some of the gases that we're interested in. And the reason, of course, they're so low in concentration is because they are very reactive, and they often absorb light, so they undergo photochemistry, and that helps to keep their concentrations low. So they punch above their weight, if you like. They play a really important role despite these very low mixing ratios. And the mixing ratios we're talking about can be parts per million, parts per billion, parts per trillion. Of course, a part per trillion is only one molecule in 10 to the 12 other molecules. And just to put that into perspective, that's the same as a single drop of water in 20 Olympic-sized swimming pools. So that gives you an idea of the challenge we face as atmospheric scientists to measure those gases in the atmosphere. And I suppose how remarkable it is that we have all of this technology available to us to be able to do those measurements, whether that's in mass spectrometry, in absorption spectroscopy, chemiluminescent techniques, and those sorts of techniques are things you'll be hearing about during the rest of this webinar series from other experts. So, of course, we can't just measure in one place if we're wanting to understand the atmosphere. We have to measure globally to really understand how atmospheric composition is changing and the processes that are giving rise to that. And you're all aware, I'm sure, of the different, the very large GAW monitoring network that there is. And this comprises stations that might be looking more or observing more air pollution activities, so urban or suburban stations. But one of the unique things about GAW is that it has these background stations as well. For example, Cape Grim here on the southern tip of Australia, measuring processes over the Southern Ocean. As Sonia mentioned, I'm the director of the Cape Verde Observatory here in the tropical Northeast Atlantic Ocean. And these background stations really enable us to measure hemispheric-wide changes in atmospheric composition because they're free from any local pollution sources. And just to give you an idea of why that's important, this is just a movie of a model output of surface ozone over the globe. And as it kind of swirls around different parts of the Earth, you can see ozone swirling around and pulsing as well, as it's formed in some areas and lost in other areas. So ozone has a lifetime of a couple of weeks, and well, depending on where it's being transported. And of course, depending on where you are, different processes, different meteorology, and different chemistry will be important. So whereas over forests, we have a very rich set of hydrocarbons, in other areas, aerosol chemistry might be important, and you can get processes occurring over the ocean that you don't see anywhere else. So all of this gives rise to this fantastically rich atmospheric composition that we need to go to all these different places to properly understand it. So I'm just going to really start with thinking about major atmospheric issues that we have in the so-called Anthropocene. So really the atmosphere, since human activity has really affected the atmosphere. Now, studies of atmospheric composition actually go back to the 1700s when discoveries of carbon dioxide and ozone, etc., were made. But of course, since the Industrial Revolution, then there's been a much bigger impact on the atmosphere. And really, I think the first topic that came to everyone's attention was air pollution. Particularly as cities like London and Los Angeles experienced terrible smogs in the 1950s, which really generated noticeable numbers of deaths, noticeable numbers of hospital admissions, and it was very clear that something had to be done about that. That led to the Clean Air Act in 1956 and other Clean Air Acts that followed that. So that was a really important piece of legislation that, you know, has been an example since that time. And very importantly as well, in the 1970s, the catalytic converter was invented. This has been called actually by some the most important invention in terms of in the automotive industry in terms of its human impact. And if you look at the VOC emissions per car now compared to when before catalytic converter, they're less than 1% of the emissions. But that of course is per car. We have many more cars on the road. So air pollution was really the thing that I suppose started off the field of atmospheric chemistry. In the 1980s, there were a lot of attention on stratospheric ozone as the ozone hole was detected, and the world became aware that CFCs were and other chlorine-containing compounds were the cause of that. Of course, now we're in a position where not only have chlorine and bromine in the stratosphere come down, but we start seeing signs of recovery of the ozone layer. So that's thanks to the Montreal Protocol and the controls that were put in place since then. I suppose you could say it was really in the 1990s and onwards that the impacts of climate change became very obvious. Probably not obvious enough at that point for all politicians to do perhaps so much about it, but certainly if you're working in this field, that's where the science of climate change really took off. And then perhaps in a way, I would say more recently, there was another focus, much more of a focus back to air pollution, partly because of the Dieselgate scandal, where it became clear that emissions of things like NO2 on the road from cars were much higher than they should have been, according to the control tests done by the vehicle manufacturers. So that really brought air pollution back into focus. And quite a lot of what we're doing now is, I suppose, these links now. We've gone to what are all the different feedbacks that we've got. There are feedbacks between air pollution and climate change. There is actually a nice video. I don't know if Claudia, if the participants of this have that video, but it might be quite good perhaps afterwards to post a link to it that GAW have made, really explaining those links very, very nicely. So starting then on air pollution, I'm sure you're all aware that air pollution leads to both heart disease and to strokes and to diabetes as well. So there's quite a wide range of health conditions, partly due to blocking of arteries and to oxygen deficiency that's caused. So this is well known. There are many, many studies showing these strong links between air pollution and health. Despite that, there have been some reports in the media to try to push back on that science, probably for their own reasons. But the science is so sophisticated now. Not only can it tell us that these links exist, and yet these links are obviously related to these Sustainable Development Goals for the UN, but the science can actually tell us about the risk, and I will get back to that point in a moment. Oh no, here we go. I missed a slide. It can tell us about the actual risk as well. So it can give us a statistical likelihood of developing a certain disease from a certain exposure to air pollution. And in this plot, we have a daily inhaled dose of PM 2.5. So that's particulate material with a diameter less than 2.5 microns. And then the adjusted relative risk according to these different heart diseases. So down here, these data points come from air pollution studies. These data points up here on the right-hand top right come from smoking. So if you like, when you are breathing in particulate material, it's like a small dose of smoking. So these kind of data really give us a quite accurate picture of the risks that we have due to air pollution. And actually, those risks are much easier to calculate than the risks to us from climate change. We can estimate these quite well. And we can actually estimate the effect globally, and we can estimate the effect on the economy as well. So if you put those health impacts in perspective, this is a history of all causes of death over the whole 20th century, so integrated over the whole 20th century, when of course population was much lower than it is today. And you can see that there are the infectious disease, cardiovascular disease, non-communicable disease, humanity, and cancer are the 5 main culprits. But actually, humanity is about 1 billion, and that humanity includes air pollution as well as things like drugs and murder. So it's 1 billion people. So about 20% of the total deaths were from humanity causes. And if we look at, we focus a little bit more in on that, you can see that air pollution was really a strong part of that cause of death. That was in the 20th century. In the 21st century, then air pollution has gone up even more, and that's just because, mainly because there are more people, there's more urban pollution, and people are living longer as well. So in terms of preventable causes of death, air pollution is considered to be the first and most important cause of preventable death, even above smoking, and certainly way above now HIV and AIDS or infectious disease. So it's a really big deal. And in fact, it's estimated that over 90% of the world's population lives in places where the air quality limits exceed the World Health Organization limits. And a lot of that is due to pollution in South and East Asia, where, of course, much of the world lives. So, is a problem still very much to be tackled. This plot then just shows the age distribution of excess mortality due to ambient air pollution. And essentially, it shows that as you get older, your risk of loss of life expectancy from air pollution increases. So the older you get, the more likely this will have an impact on your life expectancy. Although, having said that, 25% of the global mortality, according to air pollution, happens before the age of 60. So you're still accumulating that before the age of 60, and more so in developing countries particularly. So the pollutants of concern, these are the main 6 pollutants, and these are all in the Gothenburg Protocol, which tries to control air pollutants. So we have the number 1 pollutant of concern for air quality, of course, is particulate matter, particularly PM 2.5. We also have NO2, produced mainly from vehicles. I'll go into that in a moment. Ozone, of course, which is formed from the reactions in the troposphere between nitrogen oxide and VOCs. So is a secondary pollutant. We then have the VOCs themselves, and the sources of VOCs have changed somewhat over the years, and that's something I'm going to come back to later, but certainly mainly from the anthropogenic sources are mainly from fossil fuel combustion, as well as now fuels and paints and consumer products, and there are also natural sources of VOCs that are very important. Ammonia is a gas that's getting more and more attention and is predominantly from farming emissions. And sulfur dioxide is probably the gas where we've had the most success in terms of controlling its concentrations, mainly through putting removal processes on flue gas exhaust. So the SO2 concentrations have come right down, and there has been some success, certainly in the US, on nitrogen dioxide as well. So particulate matter can be formed both directly, but also secondary as well. So these compounds, VOCs, ammonia, sulfur dioxide, NO2, they all have an impact on particulate matter. So we need to understand these other pollutants to properly understand particulate matter as well. So I'm going to start talking about ozone in particular. We've already seen it's an important air pollutant, and in fact it's the second most important air pollutant after particulate material. But it's also a greenhouse gas, and it's the third most important greenhouse gas after CO2 and methane, so that's really quite a big deal. The reason for that is because it absorbs in this region of the atmospheric spectrum here between about 9 and 13 micrometers, which is where planetary radiation is emitted. So it's helping to trap that planetary radiation like the other greenhouse gases, and it does that very effectively because there aren't really any other absorptions in this region. So it's the third most important gas. And you can see that in the IPCC, the famous 8 IPCC diagrams of radiative forcing, which is a measure of the climate impact of different gases. The latest IPCC plots show radiative forcing by emissions. So you don't see ozone as a particular gas here. That's because it's not emitted directly, but it's formed from these other compounds. So tropospheric ozone in green here, you can see it because it's formed from methane, it's formed from CO, from VOCs, and from NOx. So you have to sort of add up all of the green boxes. This one here is stratospheric ozone, so we treat that differently. But if you add up all of those green boxes, you can see that the net effect of tropospheric ozone on radiative forcing is pretty substantial. And that's not the only thing. The ozone, quite uniquely, also has a very detrimental impact on crops. So when ozone enters the cells of leaves, it really basically creates free radicals that cause cellular damage, which basically makes you can see that visibly in the leaves turning yellow and this visible damage happening, and really causing a loss of yield in the staple crops that people need for food production. That's a massive economic loss to the world, estimated to be $20 billion per year. And again, it's particularly prevalent in countries such as Southeast Asia, where ozone levels are high, and those crop yields, that loss of crop yields is really important to their economies. So it's a really kind of triple whammy effect then of ozone. If you look at the trends over the 20th century, these are measurements made in sites that many people will be familiar with, some good GAW sites here, but these are in Europe mainly. And you can see that, the ozone at least doubled, probably doubled over the 20th century. And in Europe, at least, seems to have mainly stabilized since then. But that is not true if you look over the world. This is a nice plot put together by Owen Cooper and co-workers. They look at the trends over the whole globe. This is just of tropospheric ozone. And there are surface sites he's got here, but also some data from the IAGOS aircraft. So these are the downward pointing triangle ones here. and he's put them all together. And you can see immediately that where the ozone is on a downward trend in the US, in Europe, it's not really clear. Ozone is not necessarily decreasing in all areas in Europe, certainly not as much as we would like. And of course, it's strongly increasing in places like India and China. And overall, you can see this latitudinal trend where the greatest increases in ozone in terms of ppb per decade are in the more tropical regions. And that's partly because in those tropical regions, the impacts of increased emissions of ozone precursors are highest because photochemical activity is highest. So it's easier to turn ozone precursor emissions into ozone in these regions. So just going to then how ozone is formed, I'm sure many of you know this chemistry pretty well already, but of course it starts with NO2 being photolysed, producing an oxygen atom that reacts with O2 to form ozone. So you need sunlight for that as well. But in order to get the NO molecule back to NO2, you need the presence of these peroxy radicals, HO2 and RO2, and they in turn are formed from VOCs or non-methane hydrocarbons, as well as methane, reacting with the OH radical. So this is catalytic chemistry, and it needs, once you have the presence of VOCs and of NOx and of sunlight, you can create an awful lot of ozone. And that's a non-linear process. And actually these terms here give the overall budget terms for ozone. So chemical production is really large, although it's quite similar to chemical loss. And then we have exchange, where the stratosphere is a net source of ozone to the troposphere, whereas deposition is a net sink of ozone. So all of these things, well, they might balance out. If they balance out, that means the ozone concentration is stable. But if chemical production gets higher, of course, then it's out of steady state and you'll see an increase in ozone. But the main thing is that we need VOCs, we need NOx, and this is a non-linear process. So VOCs can comprise a whole load of different gases. We have the non-methane hydrocarbons, like you see here, ethane, propane, butanes. You can have, oxygenated VOCs like acetone or ethanol, and many others as well. But for these gases, the non-methane hydrocarbons, their main sources from fossil fuels. So you see a quite strong gradient between the northern hemisphere here and the southern hemisphere, where the concentrations are much lower. These graphs were put together by Detlev Helmig from a whole network of VOC measurements. And so these sort of humps here, you can see a strong seasonal cycle in all the VOCs. This is because they're lost in summer due to reaction with the OH radical. That's clear in all of those cycles. And yeah, and a very strong north to south gradient. Now, overall, VOCs, this shows ethane on the left axis and then the methane growth rate on the right axis. So from about 1980 or so, and for the following around 40 years, concentrations of things like ethane were coming down in the atmosphere. And that's mainly because there was better control over their sources due to the Clean Air Act and other acts that acted to really reduce those emissions from essentially from petrol and from evaporative emissions as well. So that was really a sort of success, that air pollution policy was leading to the reduction, slowly but surely, of those kinds of gases. However, when we started measuring ethane at the Cape Verde Observatory, we started measuring actually in 2006. And you can see that over time, particularly between around 2006 or so to around 2015 or 16, there's a strong increase in ethane. And even over that whole period, there's an increase of 13 ppt per year of ethane and 40 over that particular 5-year period. So it seems that the 40 years of declining ethane have actually come to a halt. And Detlev actually put together these plots of how ethane and propane were changing over the whole Northern Hemisphere from looking at the VOC network. So anything in red and orange is a positive gradient in ethane. And this shows how much it was changing in terms of ppt per year. So Cape Verde here was increasing in ethane between 16 and 49 ppt per year. This pattern, this spatial pattern of ethane, and there was a similar story for propane, is actually very consistent with shale gas emissions from the United States. So some of the highest trends were seen near to these sites, and really we didn't see very much in the southern hemisphere. And also the concentrations themselves were consistent with what estimated fugitive emissions of ethane and propane were from this fracking activity. Oops, apologies, keeps jumping around. So that is essentially what we attributed these ethane and propane increases in. So, you know, this activity that's really just occurring in the US right now, and possibly will occur in other countries in the future, really halted this 40-year decline in some of these gases. And the impact of that is really in the fact that it can increase ozone, particularly near those gas production regions, but perhaps more broadly as well. Now, for VOCs then, in general, one of the big trends in VOCs, as I mentioned previously, is that tailpipe emissions of VOCs, so basically mainly petrol cars and motorbikes, and also petrol evaporation, all of that's been coming down. This is actually just UK emissions here, but it's a relatively same story over Europe and over the US as well. So whilst those emissions have come down, actually these other types of sources, aerosols, glues, consumer products, all of these sorts of things like fragrances, cleaning products, have really risen in importance. And they're embedded in so many different domestic commercial products that this has now become a bit of a problem because it's unregulated right now, and sort of has become quite a creeping problem, I think, that people have not been so aware of. And just to sort of put it in context, I guess if you all wear deodorant, you probably use deodorant. If you use the spray deodorant, if you look on the can of your deodorant can, you'll see it contains butane. There is as much, in terms of hydrocarbons, a whole can of deodorant spray is the equivalent of driving a small Euro 6 car, a diesel car, for 15,000 kilometers. So it's huge, really, the amount of butane that you can get just from one deodorant can. So maybe next time, you know, you go to the supermarket, you can get solid things like that. And I think really, you know, it's a lesson to all of us that consumer products and cleaning products as well are becoming a really big deal for VOCs. Turning to NOx, so NOx does have some natural sources, lightning and soils and biomass burning. But in terms of anthropogenic sources, the main source are cars, trucks and trains. It also has a source from energy use as well. And of the transport sector here, the main contribution is from heavy duty trucks. Passenger vehicles are a lower source. However, you know, we might think that this is a problem that's going away. And this certainly, as car standards become better and better, in theory, the amount of NOx emissions from a diesel car should start to really reduce. And this just shows the Euro standard 23456 is where we are now, and how the allowed NOx emissions per kilogram of fuel have changed over the years. So the emissions allowed now are much more stringent than they were 10, 20 years ago. But this data, and this comes from David Carslaw at the University of York, shows data that they've directly taken from on the road from specific types of cars. So they're able to measure the NO2 and they are able to attribute that to a particular make of and model of car. You can see that although to start with NO2 emissions from actual cars started to come down, they barely changed at all for a while, whilst the Euro standards were still getting more stringent. They have come down a bit now on average, but they're still way higher than the Euro standard. And the pink shows a model from one particular manufacturer who seems to be getting worse. That one particular car is getting worse and worse in terms of its NO2 emissions. So there's still a problem here in diesel cars. This comes from a study assimilating satellite data from Miyazaki et al. A few years ago, and it shows quite nicely the NOx emission trends over about 10 years. And really, particularly how well, you know, certainly the eastern US has done in terms of reducing NOx, mainly from vehicles. Europe has seen a bit of a trend as well. and other places, India and China, where NOx has actually been increasing. And you can see the time series here. So the US in particular. Europe actually doesn't really have, could be doing a lot better for NO2. It's kind of dribbling around, and, you know, we could be doing better here. So whereas, you know, emissions from these countries have certainly increased an awful lot. And so when you look at this global picture of the NOx emission trends, it does actually look really quite similar to the ozone trends that we've been seeing over a similar time period, which is not surprising because we've seen already NOx and VOCs are the main precursors to ozone. And for much of the world, it's the NOx that really matters. And so you may or may not have seen these so-called ozone isoplex before. Essentially, what this tells us is we can either be in a NOx limited regime down here, or we can be in a VOC limited regime up here. And if we're in a NOx limited regime, it basically means that, let's say we are at this VOC emission rate here, around 30 or so. If we're NOx limited, it means if you increase the NOx emissions, you will increase the amount of ozone formed. So these contour lines here show the ppb of ozone that you'd expect from these NOx, from these different, for these combination of emissions. So if you're NOx limited, as you increase the NOx emission, you will increase ozone as well. Whereas if you increase VOCs, you probably won't change the amount of ozone very much. So if you can see along this contour, it doesn't really change the ozone very much. And if you're in the VOC limited regime, it means that if you increase VOCs from a particular starting point, you will also increase ozone. So in this case, in fact, you would increase ozone very steeply from around 50 or so ppb of ozone right up to around more than 200 ppb of ozone. And in that region, if you increase NOx, you can see actually, if you're in this part of the curve, if you increase NOx emission rate, you're actually going to start to decrease the ozone concentration. And this is because of the so-called ozone titration, where at this point, NO is so high that you're directly titrating ozone out of the system. And you're also converting more radicals, OH, to nitric acid. So the OH is not available to keep regenerating that hydrocarbon, the peroxy radicals that catalyze ozone production. And basically, I'll show you in a second, but when we've looked at the response of ozone during the pandemic, during the COVID pandemic, to the reduction in NOx emissions, these two different regimes become very apparent. According to which one you are in, it really determines what the response of ozone will be to the reduction in NOx emissions. So essentially, in most cases, in an urban area, you've probably got high NOx emissions. You could be somewhere between NOx, VOC limited. You're probably in a NOx limited regime. You're probably down here somewhere where NOx is high and VOCs cannot really get high enough to pop it into the VOC limited regime. In very clean atmospheres, you're right down here where both NOx and VOCs are low. Continental, you may be somewhere in the middle. And in a forested regime where you have lots of VOCs but not much NOx, you very much are in a NOx limited regime there. So these sorts of graphs are very useful to understand what differences in emissions will make on ozone concentrations. And as I said, this really is very clear when you start to look at the response to the COVID-19 lockdowns. This comes from the Bent et al. PNAS paper from last year, and it shows for across different countries the relative change in NO2, this percentage change, and the simultaneous change in ozone. And you can see from almost all countries saw a reduction in NO2 during the lockdowns or during the travel restrictions. And most saw an increase in ozone during that time. Only very few countries, including the United States, saw a decrease in ozone. And that is because these high countries over here were already very high in NOx. If you're already very high in NOx and you reduce the amount of NOx, you will actually increase ozone because you're coming back up this slope here. Whereas if you are in this region over here, so your NOx is already very low, so you're down at the bottom part of the graph. If you lower NOx, you will also lower ozone. And that's where you really want to be, because lowering NOx, you would think, would have a beneficial impact on our health. But actually, if that results in this area in increasing ozone, it may well not have that effect. Yeah, that's just a reminder of, in the United States, how you can see that they sort of are in this different region because they've reduced their NOx emissions so much. So what's the future for reactive gases? Now, of course, no one, that involves looking into a crystal ball, but people try to do that to imagine the future. And what's often now used are these IPCC so-called ESRES scenarios, which are socioeconomic scenarios to try to think about emissions into the future and what impact they will have. So there are these A1, A2, B1, B2 ESRES scenarios. The A scenarios up here are when countries make decisions based more on economic priorities, and in the B ones are based on more environmental priorities. And over here, we're more regional perspective, over here, a more global perspective. So generally speaking, the A scenarios have higher emissions than the B scenarios. And you can see that here in terms of modeling of global greenhouse gas emissions, where the A scenarios, including this blue one and the red one, are much higher than the B scenarios. And some of those B scenarios, greenhouse gases start to turn over and decline in the next coming decades. Let's hope we are there and not these A scenarios where it really will be disastrous for everybody. Now, in terms of what effects that has on greenhouse gases, on reactive gases, what I'm actually showing here are scenarios based on the so-called RCP. This is the old type of scenarios that we used. The reason I show that is you can easily see there the effect of high methane, which is the RCP 8.5 scenario. So the blue one you can see is always, this is on ozone, ground level ozone. The blue scenario is always highest. That's because that has the highest assumption of methane in the future. So most of the scenarios show Europe and North America continuing to decline in ozone, except for if methane remains very, very high. So methane is really important to control. And those in Asia continue to rise for some time before hopefully they will eventually decline. It's interesting, though, that we are in this junction where historical sources of pollution are maybe a little bit different to the ones that we've got going forward. So if we think about concerns of most industrialized countries, they'll be in tailpipe emissions from cars, they'll be from energy use, and they'll be from coal-fired power stations. But actually, certainly in the UK, if we look at the UK's clean air strategy, we don't have these two things in the clean air strategy anymore, because we're assuming complete electrification of the vehicle fleet, so no exhaust emissions, and no more power stations. We'll get rid of our last power station, and so there will be none. So we've got rather different sectors to worry about, including from agriculture, big source of ammonia and other gases, from heavy vehicles, from domestic emissions, including from heating, from wood, from fires, from domestic fires, and from these solvents that I talked about, and solvents and cleaning agents, and commercial products that I talked about earlier. And this one is from brake brake and tire wear, which leads to particulate material. So, we really, I guess we are at this junction where a number of different possibilities can arise for emissions going forward. And trying to understand what's going to happen to ozone, for example, is really difficult and probably unknowable. Because even if you understand those emissions, you've got all of these feedbacks that can occur for ozone. So wildfires will impact ozone, soil NOx, wetland methane will impact ozone, interactions with the ecosystems will impact ozone. So to understand ozone, we need to know all of these things, which is why, of course, it's really important to keep measuring them all and understanding how our atmosphere is changing. So I'm going to leave it there. I want to thank you all for listening, and I'm leaving you with first of all, a plot of our time series at the Cape Verde station, which is now around 15 years old. We started in 2006. And a particular mention to our station manager, Luis Mendes, who has been at Cape Verde all of that time, operating these instruments and keeping them going even over the pandemic period. So I want to, I guess, dedicate this talk to Luis and people like him that really, keep those measurements going and help us to understand what's going on in the atmosphere. Thank you.
Thank you very much, Lucy, for this very informative presentation. It was very stunning because I heard a lot of things I didn't know, especially about the deodorant spray and the comparison with the diesel car. This was very new to me. I think we have a few questions in the chat box I'd like to ask you. The first one is, what is, in your opinion, the most effective measure to improve air quality?
Well, that's $1 million question. I mean, particulate material, which is not directly related to the trace gases, is still a problem. We need to tackle ammonia emissions for that. But I think particularly in Europe, and I mean, it depends which. Of course, one country's air quality problems are not the same as another country's air quality problems. So, you know, from a European perspective, we're not doing very well on NO2. We will hopefully do a lot better as more and more people buy electric cars. So that should solve that problem in the next 5 to 10 years. We, however, are still doing poorly on ammonia emissions from agriculture. That's a hard one to solve. And then, but of course, if you go to developing countries, then we can be talking much more about domestic burning, domestic sources of energy. So there are those problems that maybe sound like they're easier to control, but perhaps not, because you know, each individual person, what choice do they have? But they have to heat their home and they have to cook. So, you know, that definitely needs looking after. But I think, no, I suppose looking regionally where I live, we could be tackling NO2 a lot better, and it's a bit, I suppose, it's a bit disgraceful that we know that there's this problem. However, we've kind of let the car manufacturers get away with it for a long time. But there are different solutions in different places for sure.
Thank you very much. I will ask you the next question, which is what about the recently increased use of the hand disinfection products? Do you already know what is that impact?
I mean, I suppose it's just one example of a whole bunch of other consumer products that we've got. So I haven't actually seen anything about whether or not, I would say that from my perspective, the kind of plastic waste, you know, the disposable masks, all of that, which is not an air pollution problem, of course, but that, you know, that sounds like we've got a real problem. I think in terms of emissions from any hand sanitizer, I think that's quite small, but I would say there is a large issue in these cleaning and consumer products. I'm not going to put my finger on too much, but Americans in particular use a lot of this stuff. Right. So I suppose it's one actual thing where we can make a personal choice ourselves. You maybe still want to carry on, you know, using deodorant, but you can choose different types. You might not want to, you know, you can use different ways to clean your home, or my favorite is not clean your home as much. So, I mean, I think that in terms of VOCs, it's certainly one area where you can make a choice yourself. Whereas a lot of things I feel like it's out of our control. You know, what's happening to ozone, and you know, what can we do about NO2? We still have to get to places, but on this one, you know, you can actually do something yourselves on that. And I think hand sanitizer is probably a minor contributor compared with all of those products that we use day to day. If you think about what you use in a day and start looking at the ingredients on your bottles of, you know, perfume and all the rest of it. So
thank you very much, Lucy. I take the next question, which is about the projection of the tropospheric ozone for the American South.
Yes. Well, I mean, I guess so biomass burning is going to be a big issue there. And one example where these feedbacks between air quality and climate are really important. So, you know, it's obviously it's very distressing to see these big fires happening everywhere, and quite a lot of attention now. And there was a GAW bulletin recently, actually, about the impact of wildfires on air quality. So, I don't know if anyone can put a link to that in the chat, but there was a GAW bulletin on that. And actually, some of these fires get pollutants right, very high into the atmosphere where they can hang around for a long time. So I think for those countries, it's going to be a big, it's going to depend a lot on climate and what happens with regard to wildfires. Of course, there will be urban scale problems as well, which will be more linked to what's going on with vehicle emissions and, whether there is a policy to improve air quality on an urban scale. But those things reacting together is really quite not a great mix.
Okay, the next question refers to the African countries. How can GAWTEC or GAW support African countries to increase the network of observing stations and to bridge data gaps? Do you have any idea?
I mean, that's a really great question and one that comes up a lot of times when any of the GAW community get together and they all say, look, it would be really great to have more data in Africa. It's such an important region where lots of things are happening, but with very few stations. So yeah, we need to support African countries to increase that network. I know that this is, we've talked to, Oksana, the director of GAW, about this, and they recognise at a high level in GAW the importance of this. And actually there was talk about, perhaps the senior management in GAW, making some, because in a way it's a sort of political choice as well of the country to fund those stations. And so I think there's stuff that happens on the ground where scientists can support other scientists in training and all this kind of stuff, but there also has to sort of be a political will from the country. So I think we need to tackle it in both of those ways. But I have no magic bullet, I'm afraid. It's yeah.
Yeah, thanks a lot. Then there is a question what the reference is of the figure describing the relationship between ozone, NOx, and VOCs, the one with the contour lines.
The ozone isoplex. If you Google ozone isoplex, I bet you'll come up with that figure on Google. I mean, they're classic from classic pictures that have been shown in atmospheric chemistry from Silman, I think, or David Parrish, really literature that went back to the 1990s. So you can find, they're sometimes shown in different ways, but yeah, you'll find it. If you search on that in Google, you'll find lots of examples. Some of them show ozone concentration on the contours, and some of them show ozone production, but they're all designed, in theory, you can't use them. You would have a different one for different cities, because different cities will have a slightly different way that ozone respond according to how much sunlight they have, for example, or other situations. So you can't use the same graph exactly for every single place. You kind of can use modeling to generate them. But yeah, you should be able to find them online.
Okay, thank you very much, Lucy. We move to the other question, which is about the impact of large fire in Australia, which is the issue seems to be that the rise in how do you think this will contribute to change the air quality in the changing in climate? And here I think the northern atmosphere, the northern hemisphere.
Yeah, I mean, it's going to be very detrimental to air quality, as we've seen in these places where it's happening. I heard a lot about fires around in America and Australia, and there's studies already showing that they have this detrimental effect on air quality, mainly through production of small particles, biomass burning particles, that not only are bad for air pollution, but they absorb light, so they're bad for climate as well. So it's a really important issue that's going to get almost inevitably get worse, I think, with fires. I mean, even in the UK, in the North York moors, where normally we just have so much rain, even up here, we see wildfires now over the summer season, and these great piles of particles that you see with that. So yeah, definitely, it's something that is a major, more and more important issue in the future.
Okay, we're moving on to the next question. Is the AOD a good indicator for air pollution?
Well, so the aerosol optical depth, well, it depends, because the aerosol optical depth, of course, is the whole column above your head. If most of those aerosols are in the surface, then that tells you that you've got a lot of aerosol at the surface, so that's going to be correlated to air quality. But if the aerosol is like in a layer above your head, you're not breathing that air. So it really depends. Like, for example, measuring at Cape Verde, sometimes you see these so-called Saharan air layers where the dust comes from the Sahara. Sometimes it's lofted up and it goes across many kilometers in the air. And sometimes it comes down at ground level. So you would see the same in AOD, whether it was higher up or lower down, but of course it's only when it's transported lower down that it impacts air quality. So you can use it, but you sort of have to know, what sort of aerosol it is and where it's located in your column as well. But yeah, it's a kind of, because it's used in lots of, there's a lot of measurements of it. So it's a good way to sort of see a global picture of where air pollution is.
And the next question moves to the climate. So how reactive gases affect the climate, and then also do reactive gases affect cloud formation?
Yeah, I mean, well, hopefully you'll all click on that link that Claudia sent, which gives that nice overview of how reactive gases affect climate. So I'd encourage you all to do that. But yeah, in lots of different ways. I've mentioned mainly how, of course, there's ozone itself, which I've talked about, which directly impacts climate because it's a greenhouse gas. But ammonia affects particulate material, as does ozone, as does NOx, and anything that affects particulate material will affect climate. And of course, ozone and NOx affect the concentration of the OH radical, which is the main sink for methane. So there are all of these interactions which are very hard to separate. So yeah, they directly do impact climate. In terms of cloud formation, yes, as well, because I mean the major thing we all think about, I suppose, the classic example is SO2 emissions forming sulfate aerosol, which then forms cloud condensation nuclei and clouds. But there's lots of these interactions, and I suppose if you think about it, it used to be, if we go back many decades in atmospheric science, you'd have a gas phase people, and then you might have particle people. And what we really have come together over the last maybe 20 years is a huge amount of how those interactions happen between the gas and the aerosol phase. And there are so many interactions, and they're very complex. And it's taking us all this time to really understand them, but it's a really good challenge, I think, in atmospheric science.
Thank you very much. And then we move to the last and the final question we have here. It is what would be the best model technique to examine the ground based on PM 2.5 using the satellite AOD?
That's a good question that I'm not qualified to answer. I'm going to basically say I really don't know. So I'm not a satellite expert, and I'm not a particulate matter expert as well. But maybe Claudia can put you in, or somebody could put you in contact with somebody that there will be people within GAW that know the answer to that. But sorry, I can't help you on that one.
Okay, thank you, Lucy, for being here with us today, doing this presentation and answering all these questions. That was really great. We like to close the webinar now, and we also like to introduce our upcoming webinar. The next one is on the 20th of October, the same time. It's with Richard Olof Ruud, and he will tell us how to submit data to EBUS. He's from the NILO, the Norwegian Institute for Air Research. We put the registration link in the chat box, and thank you everyone for being here today, and we hope to see you soon in October in the next session. Bye.